Excellent. So, in order to give you an idea of the work we're doing, I set up this adaptation to high altitude, the paradox of tolerance to hypoxia formula, one small step by a giant leap in biospace forming. Now, all I do, I was educated by my father to always create. This is what I was born to, a school, an academia of creation. We're always thinking. So Natalia and Rafaela are being trained in that sense also. We have liberty of thoughts. Like, what's changed? No, not changed. Which one is changed? Which one is changed? Okay, yes. So, very briefly, there is sea level. Pointer, do I have a pointer here? Oh, okay. So this is sea level, 760 millimeters. In La Paz, you see, we are on a mountain, 495 millimeters. That's where we are located, in the city of La Paz. So of course, the pressure, the back, you see the pressure of the atmosphere. At sea level, when we come down to sea level, we feel the pressure of air. It becomes a little heavy for us to breathe because we are used to molecules being more separated. You see, the oxygen molecules, the nitrogen molecules are more separated. There's less pressure in the air. And so, this is to show you that we start at sea level with 760 millimeters, and we go up in an exponential manner with the altitude or the barometric pressure. And we have here different, the city of La Paz, right there, Chacaltaya, Sahama, and Everest. This is a very original pointer. The first time I've experienced it. So, you see the oxygen saturation curve is one of the marvels of biology. Did you realize that it carries the most stable element on Earth, which is iron on it? This means nature has provided the most fundamental stable element. If you look at the graph of stability of elements, you will see that the highest peak is reached by iron. So that element is in the molecule. Because life on this planet, so far, it has not been discovered elsewhere in the universe. We should have already gotten some signals. Because we have signals from the beginning of the Earth, from the Big Bang. So why are we not getting, if there's intelligence elsewhere, some sound? Maybe we are alone. We are completely alone in the planet. And so these marvelous molecules are providing the oxygen to the tissues in an extraordinary way. And you see here, this is the saturation curve. And here is sea level. And as you go down, it's La Paz. Chacaltaya is where we have a laboratory at 5,300 meters. This is Sahama, where we have a soccer game we have played at 6,500 in Mount Everest. So you see they are going down. And what I am observing in much of the literature around the world is that people don't understand these pressure changes. If you are in La Paz and you put on a pulse oximeter and you take a deep breath, after a little while, your saturation from the normal value of 91% at sea level goes up. In La Paz, 91%, it goes up to 98 just from taking a deep breath. The reason is as you reduce the dead space, you increase the amount of pressure in your chest. And I'm going to give you, I have so much to do. I'm giving you some original ideas that we are going to do some more research on. So, please go ahead. And so, the next thing is, what causes most deaths on the climb of Mount Everest? One is tempted to affirm hypoxia. because people say, oh yes, people die in Everest because of hypoxia. However, if you see this, when you look at the death on the mountain, you can see that there is statistics for how many people have died at what levels. And above 8,000 meters, you have the death zone. It's called the death zone. There you are. So this is where people die, mostly. And they mostly die coming down from the Everest. You see, if you look at the amount of deaths because they fall, because they freeze, because many other things happen around. When you truly look at the hypoxia, it is only 9% of those that die on Everest that may be due to hypoxia. But you must consider that these people have not been sleeping well for very long. They are very tired. Their food has not been well absorbed. So once they do reach the high levels, they tend to have more complications. So it's not only the hypoxia that's producing this. So that's why my father proposed, partly that's why, also because of the fact that people with chronic mountain sickness in the city of La Paz can come because of their lung diseases to our consultation room with a PaO2 of 30 millimeters of mercury. And they walk into our laboratory and say, well, I'm feeling a little sick, and you go, well, okay, let's see, with blood gases, 30 millimeters of mercury. Oh no, something's wrong. Run again. We run again, 30 millimeters. And he says, I'm feeling a little sick. And this is the pressure on the summit of Mount Everest. So that's why my father said, you know, these people are living at sea level, but because of their lung limitations, their ventilatory insufficiencies, they are tolerating very low levels of oxygen. So Mount Everest, man can adapt to this, live even at the summit of Mount Everest if you're totally healthy, if you go up slowly, if you have comfort, if you have a 5-star hotel on the summit of Mount Everest with heating, and you gradually go up, you will make it. That was his theory. And it has shaken the world because many physiologists thought that people only can live up to 5,000 meters because that's where there were populations. But the conditions of cold were there, of course. I'm sorry, how much time do I have left? I need to make sure, because I have so much material I want to show you. How much time do I have?
40 minutes.
40 minutes, okay. So, here you see, we are at sea level with a pH of 7.4 and 40 millimeters of mercury. So, as we go up, we increase the PiO2, the inspired oxygen tension. We increase ventilation. Carbon dioxide goes down, pH goes up. Of course, and that's called acute respiratory alkalosis. Renal excretion of bicarbonate then produces a compensation, and we achieve a compensation where our pH of course is 7.4 and PCO2 is 30 millimeters. This is what we call a totally compensated respiratory alkalosis or chronic hypocapnia. So the total estimation of people living above 2,000 meters in the world is more than 200 million people. Is it possible that 200 million people are living with an acid-base status of chronic compensated respiratory alkalosis? No. How could you say I live in my country and with 200 million people, in the high altitude, all of us living in a sick, unstable, acid-base condition? So we have said that high altitude residents are living under normal conditions for their environment. Let me tell you, this is from a couple of years back. They measured blood gases near the summit of Mount Everest, team from England. And you see, they found that the PCO2 was 13, their hemoglobin, the pH was 7.43, and look at the oxygen levels, 24.6. And they interpreted this using the Fans-like equation and using the sea level equation. But with Professor Paul-Erik Paulem, I worked at the University of Copenhagen as visiting professor. We developed formulas, and this is what was called the base excess or base deficit of the Fine-Slack equation. It's the balance of pH, of acidity and alkalinity. Cells have to work in the perfect pH, otherwise all, as you as biochemists, you will understand that if the pH is not optimal, the metabolic, enzymatic activities get totally out. So we named it titratable hydrogen ion difference with Paul-Erik Paulem. And it is ideally determined by titration to a pH of 7.4 and a PaCO2 of 40 millimeters of mercury at sea level. You see, it's at sea level. It's saturated and at flat temperature. So, this is Paul-Erik Paulem, a great colleague. We were discussing here, you see hydrogen ions in the acid-base status, where it was all created a while back in Copenhagen. And this is Ole Sigurd Andersen, the man that created the graphs that I'm going to show. So what we did is we described how to adapt this formula to interpret acid-base at different altitudes. And I worked on this much deeply into it, and I realized that in the formula you have hemoglobin in the formula, which is part of this, and also you have the actual bicarbonate. So I made correction factors establishing the altitude hemoglobin and the altitude bicarbonate, and therefore with this I could come up to a correction to this acid-base chart. You see, that's the normal area there for a pH, for a PCO2 of 40 and a pH of 7.4. And when you get out of this normal area, you are in the different acute hypocapnia, acute hypercapnia, all the alterations of acid base. And if you are in La Paz, our CO2 is 30, right here. So we were right when you use these charts. And they still use them. They don't understand. That's the problem when you are thinking far ahead. People don't understand. So, you see, in La Paz, we were here in chronic hypocapnia. So we were completely abnormal. So I decided to look for that, change the thing. So here is from 2,000 to 2,900 meters. I moved down the scale because to the values of CO2, and then for the city of La Paz at 30. And now we are in the normal area. That's how it is, okay? And now, let me tell you, if we go to Mount Everest, the CO2 is down here. So this is completely a different level, but the balance has to be there. And so, when I looked at that paper, I said, if acute adaptation to altitude is achieved, the acid-base status of blood changes and becomes normal with no alteration for base excess or base deficit. There can be no base deficit under normal conditions of adaptation to high altitude. In other words, complete acid-base adaptation to high altitude implies a normal acid-base status for that altitude with no deviation from the norm. So, if we use the sea level formula, you see at different altitudes like La Paz, we had -5. And at 4,500 meters, this is the data from the Everest. They found it there. So this is, their interpretation was totally wrong. They calculated using the sea level formula, and these guys on the summit of Mount Everest had a base excess of -7 millimoles. You cannot be on the summit of Mount Everest in hypoxia with this condition. You would be in intensive care, you know? So I used my formula and I calculated using their data, and look, it's almost zero. It's in balance. So actually, the people in the real acid-base status was subject at 8,400 meters. This is why the extraordinary mountaineers are able to survive and continue to perform exercise even at those altitudes. This is fundamental. I just got a review paper, and they don't understand it. And these are top medical universities in different countries. Now let me show you the breath holding test we developed. I developed equipment in our institute, and this we developed with my father many years ago. This is a pneumopack. You're measuring carbon dioxide with this scale. The red line is the pulse oximeter with values. This is the pneumopack. This is the end-tidal CO2, and this is the pulse, the white one. You see, so they're breathing normally at around 30, 20, 27 PCO2, which is normal. And look at these variations of the saturation from 95 to 85 from just holding your breath. There's great variation because it's not in the plateau of the oxygen dissociation curve, it is in the steep part. So this is a person like me with a normal hematocrit, 50%. This is his breath holding time. So what happens with somebody that has increased polycythemia, which was called increased polycythemia, then excessive erythrocytosis, which means you increase red cells due to different lung diseases, different heart diseases, many organs, which Natalia will probably give you some of that. And so we find a patient with 75% hematocrit. He comes to our clinic, we run the test, and you see we have him hold his breath, and you would think these people are completely despondent, they are very sick. Most of them are doing quite well. They are adapting thanks to hemoglobin. And look how long he can hold his breath. Longer than normals. This is more or less 2 minutes time. And look at the variations. His saturation is quite low because he has lung diseases. Then when he takes a deep breath, saturation goes up high. But then look how low it can go. In this case, it was around 70% saturation from just holding his breath. And then after that, he takes a deep breath, and look how oxygen goes all the way up, and then he goes back to his stable but lower saturation. This test has given us a lot of information of pulmonary function at high altitude. It doesn't, actually it's made for high altitude. It's not a sea level test because you wouldn't see these variations. Now, if we have the hemoglobin and we study how these populations at high altitude, what their hemoglobin is in the Andes. By the way, I am coming up with some theories that I want to work with Ishmael Tassi regarding the Tibetans' higher saturation levels being found. We have to reanalyze what is being included in it, and I'm going to explain that later on. So, you see hemoglobin starts going up, up, up as you go higher out. And we did a trend, and we would say, well, more or less Everest, there would be very high hemoglobin levels. But what is evident is that in the Andes, we have more red blood cells, more marvelous molecule hemoglobin that allows us to survive in hypoxia. Then I observed another variable that changed with altitude. Carbon dioxide. At sea level, it was 40, like you are right now. In the city of La Paz, 30. And as you go down, all the way down to the summit of Mount Everest, they estimated around 8 millimeters of mercury of carbon dioxide. So this is a parameter that's absolute as you go up. And this gave me the idea, along with the distribution curve of carbon dioxide in 1,865 patients at 3,510 meters. Look at this. This is around, we have around 30, like we told you, but this is the distribution. But look, we hardly ever, we had one case of 61. Well, these were terminal, they were literally dead at 60, about 61. But look how few cases, and some of these were intensive care patients. We don't have the values of high CO2. So I concluded that we had to look at these PaCO2 values going down, and of course the oxygen tension going down, and how could we interpret the tolerance to hypoxia? And I came up with this formula. Tolerance to hypoxia is equal to hemoglobin R over carbon dioxide. Why? Because the more hemoglobin you have, the more tolerance to hypoxia you have. You can live higher. And carbon dioxide, the lower the carbon dioxide it is, the more tolerance you have to hypoxia. This is fundamental. And if you see here in this formula, which has a factor, this formula is transcendental because it shows you that you can tolerate levels of hypoxia better the higher you are. Paradox. Again, nature has shown this. Now look at this. This part is ventilation and this part is the oxygen transport. Two fundamental pillars of transport to oxygen to tissues. And this is how I developed the constant there, equating the sea level values to 1 and then estimating what it was at different altitudes. And so we see here that at sea level, if you have the value of 1 tolerance to hypoxia, you go up and it begins, this is the city of La Paz, we have around almost close to twice the tolerance of hypoxia, and then in Mount Everest, almost 6 times more tolerant to hypoxia. This is paradox, because you would think here, if any of you suddenly drops your PaO2 to 60, you will probably end up in intensive care. But we, as soon as we put you all on a plane and you arrive on that flight, like Professor Kusal Das has done, and Professor Biradar that have honored us in our symposium, they arrived in the city of La Paz. They already, if I took blood gases, I measured their PaO2 would have been 60. And they were walking around and they did quite well. And they both did quite well. So that's the paradox. So my father named the 2 pumps of the organism, the pneumodynamic pump, that which moves air, the movement of air in a gaseous state, and the hemodynamic pump, the pump that pumps blood, a fluid. And these two have respiratory rate and heart rate. You see, similar. Tidal volume and stroke volume. And they both together, if you multiply those, you have cardiac output. If you multiply those two, ventilation per minute. And these two work together to help you adapt to high altitude. But what happens? In the initial phase, when you arrive to high altitude, you don't have the hemoglobin. So they have to work. They 2 pumps. But as time goes up, your hemoglobin goes up, then the hemoglobin takes over the role of these two, and that's the marvelous molecule that allows for us to reduce our ventilation, because otherwise we would be living like this in La Paz, and we don't. We breathe practically normal levels, so you see. And the tolerance to hypoxia formula that I was telling you has to do with the factor of ventilation and hemoglobin. By the way, this shows you that the cardiac function can help by improving a little bit your cardiac rhythm. But the fundamental part of adaptation has to do more with ventilation. The role is fundamentally more played by ventilation and carbon dioxide. And by the way, you see in this tolerance to hypoxia, we don't have the variable oxygen. And you know, I gave this talk in Italy now. One of the professors of the University of Milan came up to me and showed me his lighter. And he said, it's not in the oxygen, it's the carbon dioxide. He had a lighter that his students had given him because he insists carbon dioxide. So carbon dioxide is going to play a major role in the understanding of hypoxia. So, with all this, I have to tell you that biospace forming is a word I created to explain that once we go into space, and by the way, you're all invited to, I have to give a talk about space travel under a chronic hypoxia environment, and I'll do it tomorrow. Where is it? 2050. 2050, yes. Oh, maybe you won't be here. But sorry, but I can give you a link to YouTube. The talk is on YouTube. I was invited by NASA people to a space symposium to present this work in May this year. In fact, in our next chronic hypoxia symposium, we're going to have the NASA scientists can participate with the Space Symposium in Electronic Hypoxia Symposium of 8th April. So, biospace warming is the adaptation of all living beings on Earth to space. You see, once the scientists at sea level are planning terraforming. Terraforming means they want to change the planet Mars to become like Earth. Terraforming, which is quite wild. I mean, almost playing like a god, because it's difficult. The temperatures is farther away than the Earth from the sun, so it's colder and it's very complicated. So I looked into it and I said, well, they are forgetting the other factor, which is biology. Biology has to also adapt. So that's how I created this word, biospace warming. And let me tell you that I published this paper, Space Travel and High Altitude Environment, one more step in human biospace warming. BLDE University journal. Okay? And this is a first in the world. And let me show you why. Because I checked, after I published, I checked in the web, oh my God, maybe somebody already spoke about biospace. So I put biospace warming. Only one citation in the whole world was there. And that's BLD University House. So, in India is where this word was created. And you will see how it will spread, not only on Earth, around the universe. Isn't that nice? Thanks to him. He supported it. So, the conclusions for this talk, I have a lot of material to show you, but time, of course, must be, we're almost done with time. And so, let me tell you, since our new facts-like equations operate with normal mean values for PaCO2 at the actual altitude, a calculation of THID will always result in normal values, THD 0. THD 0, or basic sexual base density should be 0, or close to 0. This is the balance optimal for cell function. These charts have been developed for different altitudes. This will help in all intensive care units and significantly improve the recovery of critical patients in hospitals at high altitude around the world. The tolerance to hypoxia is higher at high altitude. This is a paradox, but it's real. The tolerance to hypoxia formula allows a quantification based on two essential biological responses to hypobaric hypoxia. Hemoglobin that increases, PaCO2 that decreases. That's why we have this formula. It's not understood yet. Unfortunately, it takes time for people to understand. The Mount Everest or any altitude analysis of blood gases has to be carried out considering the normal altitude carbon dioxide for that specific altitude. Never should a sea level facts-like formula for the acid-base status of blood be used at high altitude without the modification here I've described. Mountaineers' acid-base status with a THID of 0 is essential for reaching the summit of Mount Everest. Chronic hypoxia is the first step in a giant leap towards biospace warming. So I invite you to my next talk, which shows that you should, space travel should be in an environment of high altitude. Because biology helps surpass a pressure. This is the first time, I don't know if any of you have heard of that, where biology can help break the limitations of pressure laws of physics. Because the pressure laws of physics are set, you cannot change them. You see? And so it is quite amazing that, let me tell you that I just saw yesterday that the spaceship that Elon Musk is making